You won't believe it. There is also a security industry before IoT came up. And I'm coming from the security industry, working 25 years in the area of security, mainly in the area of smart cards, secure operating systems. And I want to show you a little bit why many things are currently changing in the security industry. So, because we go from extra security, which is in a separate chip located, towards highly integrated security solutions. I think you have heard this in the previous presentation. Already implicitly it was assumed that the security solution is bundled together with the whole device, with the whole system on chip. In the smart card industry, actually this is not the case. So there are currently a lot of things changing related to former security paradigms with the new security paradigms of IoT. And I want to present you a little bit what is the game changer here, what is currently happening. So first I will compare a little bit the classical secure element-based security versus the system-on-chip integrated security. Then I will speak what new architectural concepts are required for secure operating systems when they are SOC integrated. Then I will speak about the importance of root of trust. Of course, you have heard this already a little bit in the previous presentation, or in a lot of detail even. And then I will speak also about remote management via a well-established root of trust. But this is a general overview. When you take currently still a device, so take your mobile phone, then your mobile phone has your main application system on chip, but there are also separated secure cores in the operating system. For example, the most famous secure core is the SIM card, so it's a separate security controller with the SIM credentials on it. But there are also payment chips, for example, in your mobile phone to enable payment, etc. So this is the architecture which is still a lot of use. The future, and IoT is already arrived there, are integrated cores. So this separate piece of silicon will migrate into the complete system on chip, and the security will be a part of the system on chip. And this is a big change because in former times it was easy. You can safeguard, control, make tamper resistant a separate secure core, but you can imagine such a separate secure core has also some drawbacks, such as high handling costs for such a secure. You have additional costs of this piece of silicon. So here this solution costs and is difficult to handle. This solution, when it's treated in the right way, can be a very efficient security trust anchor in the system. So, and I want to present to you a little bit what is changing with the operating systems which are executed here on that secure core or on that secure core. So the classical smart card industry is a very well-established industry over almost 30 years. So everything in a SIM card or in a credit card, payment token is designed around a low bandwidth ISO interface. This low bandwidth ISO interface is sufficient for authorizing transactions or authentication to mobile networks, but it's a little bit old-fashioned, more than 20 years old. Then all security is grouped around a single-threaded OS without any multitasking capabilities. So when you look at the standards for secure operating systems, which is mainly done by Java card standards, the classical Java card standard is a single-threaded system. Then these security measurements against side channel attacks, fall injection attacks, or tamperings are done in a very closed job. So the chip is hardened already against these attacks. So the processes like the common criteria, evaluation, or in former times it was the ITSEC criteria, are established over many, many years. And it's known how to harden a dedicated microcontroller. Third-party execution on such low-constrained systems are typically done via a Java virtual machine abstraction layer. So, and the aim of such a secure smart card OS is actually to ensure integrity of transactions and protect keys, and of course have a lot of state machines, security controls, etc., which require frequent access to directly onboard non-volatile memory. And the whole smart card is processed in secure manufacturing lines, which starts already with security measurements during silicon manufacturing. So security controllers are typically not manufactured on generic purpose manufacturing lines. They are done on special manufacturing lines. The individualization and personalization is done in high secure environments. So it's a whole industry grouped around this processes. And you can imagine these processes are not cheap. They cost. So with integrated security solutions, things are changing here fundamentally. So first of all, the OS is no longer on a separate chip. It's in a complete system on chip located. So, and the system on chip has high bandwidth I/O capabilities. You all know this probably memory mapped I/O, mailboxes principles, etc., where you can exchange with the security environment with a high data rate data. So in addition, a single thread operating system is no longer sufficient. So you need multiple applications have to be supported either in a mobile phone, in a rich OS, or in the real-time OS of an IoT device. So you need concurrent security support, and you cannot rely on a single-threaded operating system. So another important change is the secure OS is booted together with the whole system on chip. So the whole system on chip boots up. I will have later a picture on that. And so the root of trust and the boot of the whole system becomes crucial for security. Because when the root of trust is not well settled with the system on chip, then even the best secure OS has no value. The best secure OS can be circumvented, can be tampered. So secure trust and a trust anchor in the boot is very important. Then, of course, companies are thinking about special measurements, how to make a generic production line in silicon secure. So I think in previous, the ARM platform security architecture was mentioned. So the latest step of ARM is to harden security controllers already in the design, like the Cortex M35P processor, for example. So already the design becomes hardened. So to overcome the challenge with silicon manufacture, to make a special silicon manufacturing line. And of course, these generic purpose silicon or devices cannot be treated in high security environments. You cannot imagine that every IoT sensor is going to an extreme high secure manufacturing line. So it's really important that a root of trust already on silicon level is established, which can then replace the later secure treatment in special manufacturing lines. I will show you later how this can be done. So a few new architectural concepts are required for SOC integrated secure OSs. So one concept which is already since a few established in the industry is microkernel-based concepts, like as the separation kernel. L4 architectures are very widely used already as a security foundation on OS layer. So another security principle which is also established, especially with larger chip architectures, such as the Cortex-A series from ARM, for example, is a memory management unit. But in smaller devices, in smaller constrained devices, even a memory protection unit is essential for isolation. And of course, the previous mentioned root of trust for the whole SOC needs to be established as early as possible in the life cycle, because after this establishment, you can later do remote management in a secure way, and you are no longer relying on the environment in which you do the security management, because you can establish a confidentially protected channel towards the device and transmit data end-to-end secured from the managing entity down to the device. And anything in between doesn't matter, actually. So then measurements against side channel attacks of the security subsystem are still very relevant. So you can do this even in scenarios where we have a complete SOC. So you can do metal shielding, for example. This is still possible to do with system integrated security. And last but not least, so you need performant communication channels between security enclave and other SOC components. So one example where such a performant communication channel is currently established is with the encryption and decryption during content protection. So when you watch a movie on your device, then you have a high data rate stream on your device, and it's on the fly decrypted on your device. And this is done via a high performant memory mapped I/O on your mobile device. So that's actually the root of the trust zone, this content protection. So technologies such as the Play Ready, for example, use this kind of mechanism. So here a little bit in architecture. I hope it's not too small and you can see it. So the foundation is the several times already mentioned root of trust. The root of trust in principle holds the private public key pairs which are required to secure the whole device. I will later come to it a little bit. Then you have the secure boot, and the boot typically forks. You have the boot of the secure environment. So you have a secure OS boot, then you have a secure OS kernel, and you have on the OS kernel running different services. And then in an IoT device, you have the real-time OS boot. So this boots up your embedded OS where you have the normal applications. And the normal applications are supported by certain services, for example, an encryption service for encrypting data in a TLS format by a service in the secure world. Other things are such services can be, for example, also an integrated SIM card. So you might have heard already about this technology, about integrated SIM cards. So currently a lot of people speak about embedded SIM cards. Embedded SIM cards are still in a separate chip, somewhere soldered into your device. An integrated SIM card, in principle, in future, is such a service running on a kind of secure OS kernel. And all, of course, needs to be also hardware secured. I think not very much people believe in software-only security, so you need a secure core. And this secure core can be either an ARM trust zone for Cortex-M, it can be a Synopsys ARC-SEM processor. There are many variants of hardware security actually available, but you need some hardware secure core where this world is running. And the other CPU cores are typically then for the applications used. So typical security functions which are anchored in a root of trust are the verification of the system on chip, the device and identity, and also the integrity of the device itself. Another thing is integrity protection can be executed on all layers on the stack. So it's important that your security services are integer, that the kernel is integer, that the boot is integer. So, and this integrity protection also during the loading, the runtime of new code, or even when you change or modify services, then it needs to be still verified. So when you look at the current approaches of integrity verification, then one of the most famous is the Trusted Platform module, for example. And it started by measuring the integrity of the system during the boot. But that's not sufficient. You need to measure continuously integrity of the system, because at some point you also want to modify the system. So you need to, after modification, you need to restore new integrity values, and you need to continuously measure them. Then another thing which is very important, devices are personalized. Even IoT devices are assigned to an organization, are assigned to a person. And this personalization process is in many cases also used for billing purposes. So personalization is a very critical process because it assigns a device to some billing entity. And it's, a billing assurance is a very important aspect, not only with SIM cards, where it's obvious, where you're billed based on the services you consume, but also in other scenarios. So personalization is an important step. Of course, also mentioned in the manufacturing of the device, you want to efficiently prevent gray market devices and overproduction prevention. So a root of trust can be also used for this purpose. Then a root of trust typically is used for an end-to-end secured communication. So in typical communication protocols, not only the TLS security, you have a kind of handshake in which you verify the identities, either mutual authenticated or at least one side, server-side authenticated. And in such scenarios, you need to have a kind of root of trust certificates, as previously mentioned. And then another aspect for a root of trust is actually the administration of an IoT device or any device. So IoT devices have a much longer lifetime than your mobile phone. Typically, your mobile phone you exchange after 3, 4, maybe 5 years. But some IoT devices, a car can live 10 years, a parking sensor in the tarmac can also live 10, 15 years. So IoT devices are seen to live very, very long. So you need to bury in the ability for updates, configuration changes, or even crypto agility, as previously mentioned. So you might at some point, new algorithms might be figured out, when you see the hype currently on post-quantum computing, what can all happen with asymmetric algorithms. So you might want to update maybe at some point cryptographic algorithms. So you need to have the capability to modify, change devices, and the root of trust, therefore, is essential. And last but not least, of course, at some point you want also to delegate rights to third parties to manage a device. So also the root of trust can be used for delegation of management. I will show later in a few scenarios how this can be done. I have selected a few security functions for remote management and want to show you how you can implement the security functions with help of a root of trust and with help of cryptography. So again, a little bit cryptography, but don't worry, it's not about PKI, it's a little bit about asymmetric cryptography, and it goes really on a high level, so I think it's not too difficult. The easiest one is to prove the identity of a device. To prove the identity of a device is done in such a way, typically the device holds securely a private key, the root of trust forms this, or the private key is a part of this root of trust, and now you want to verify that you are really exchanging data with the right device. So you send a random challenge. The random challenge goes to the device. The device signs the random challenge with help of this private key, and somewhere out you have the public key. The public key is known to everyone, so with help of the public key you can decrypt the sent random challenge, and you know only the entity who owns this private key was able to encrypt the challenge. So it's the easiest way of device identification. Typically identification scenarios boil down to this scenario, that you have somewhere a private key, send a random challenge, sign this random challenge with the private key, verify it with the public key, which is outside somewhere. Now, when it comes to authorization or authentication scenarios, it's exactly vice versa. The public key is now on the device, and the private key is somewhere outside. And in this scenario, the private key is used to sign data, code, or any administrative action which triggers a change on the device. And the device itself is able to verify if this is a proper data, code, or administrative action by help of a public key which is in each and every device. So this public key is typically device individual, and so for every device you simply send down signed a command. By the way, this public key is a public key, so no confidentiality protection of this key is required. It needs to be just integrity protected, so no modifications should happen to it. But so it can be somewhere fused, put in the fuses of a device, or the hash value of the public key can be put in the fuses of the device. Now, the next step, a little bit more complicated. Again, the private key is on the device. Now you want to send confidentiality protected data to the device. You don't do this with direct encryption of the public key, because asymmetric schemes are not so performant for data encryption. So typically you choose an ephemeral temporarily transport key. You encrypt with this temporarily transport key the data which you want to send to the device, and then again you encrypt with this transport key by the public key which is outside, so you can be sure this data which you send down to the device is only readable to the device. So it's a two-stage principle. First you encrypt with a randomly chosen symmetric key the data you want to send to the device, then you encrypt the randomly chosen key by the public key, and now you can be sure only this device which holds the corresponding private key can read the data. It's a typical hybrid scheme used in many scenarios. So typically here we have such a scenario. We have device provisioning. So we also want to send new code down to the device. So code confidentiality needs to be required. So we choose this. We choose again a symmetric encryption key, again an ephemeral encryption key. We send this with a first message down to the device, and in a second message we can encrypt with this key the code which we want to send to the device, and in addition we can sign with encryption key. I need now to think what I was thinking. Exactly. So you send down with the device. It's actually the same procedure as in the previous one, but with two commands. So first you transmit in a secure way the symmetric key, and afterwards you use the symmetric key to encrypt data. So it's split up in two command flows instead of one as in the previous slide shown. And the last slide is the delegation of rights to third parties. Also an important aspect. Imagine the ownership of an IoT device is changing. So when the ownership of an IoT device is changing, you might want to authorize a third party to do management operations. So you have a kind of master private key, and with help of this master private key, you can sign private keys of third parties. So you can establish in the device itself a new third-party private key, and this new third-party private key is then used for management operations by the third party. So also a typical principle widely used in the industry already for delegation of right. It can be, by the way, also used for crypto agility. Imagine the crypto algorithms are expiring. You want to switch onto new cryptographic algorithms. So you can download for the new algorithms the necessary public keys. And afterwards, you can then invalidate the old crypto scheme and maybe even the old master key. So such schemes where we register new keys by help of one master key public are widely used for third-party management operations. So now my summary. I know it was a bit a mixture between different technologies and I think it captured a lot of topics, but I think you are quite familiar with technologies. So the summary, what I want to give you, the raising of the next generation of system on-chip integrated security has an impact on the whole security industry. So there is a paradigm shift with the secure OSs, the silicon architecture, and of course the related processes. So for some companies who work in the root of trust area, I think there are new opportunities which will show up. But on the other hand, this will also change the existing security industry, because I think no longer the bunkers and the secure manufacturing lines are required, because security will be integrated with the silicon and different processes are required by treating this integrated security. Thank you, Stephan.